So today, I guess, is the last part of our section on multi-phase fluids. We said that we're using multi-phase fluids because that's what exists in these difficult problems that we're going to deal with. And what we'll talk about today is kind of an extension of that, and that is really in talking about the behavior in the vadose zone. And so in that we'll talk about how agronomists talk about flow in the subsurface and how it links to the terminology that we use. We'll talk about some empirical relationships that describe capillary pressure saturation curves and permeability saturation relationships, which we've looked at already. And these are by two sets of researchers, Brooks and Corey, and a guy called Matrinus van Genuchten, who's originally Dutch. And so, recap first, I guess. Perhaps don't need to do this ad infinitum, but this is kind of the summary, really, of what we've talked about so far. We can describe this behavior in terms of the saturation with depth in terms of this capillary pressure saturation diagram. You're doing the curves for that right now from some lab data, I think, for your current assignment. And it says what the saturations of the two... Jesus Christ, wasn't it doing this last Tuesday? Pardon my French, of course. And you know that in this represents the saturation of the non-wetting fluid, and this is the saturation of water in all of this. And so, depending on the capillary pressure that you find yourself at, or equivalent of depth you find yourself at, you can describe exactly what the saturations are. And those saturations also define the magnitudes of the relative permeabilities, which allow you to say how quickly fluids would be traveling in the subsurface. You're going to use this for your question 2, assignment 3 question. Relative permeability will be 1, right, because it's fully saturated with water only. You'll use either permeability or viscosity. This is the relationship that we just talked about that allows you to convert between them for pressures and heads, etc. And this gives you a volumetric flow rate, and you can convert a volumetric flow rate into a Darcy velocity, and you can convert a Darcy velocity into an advective velocity. So, and you can probably work out what the porosity of something that has a height S of solid rock and a height B of open pore space. The porosity is going to be the ratio of those two terms. So that's one thing that might happen. So we've developed this. The other thing and we've talked about how these relate to each other, because we think about flowing between the pore space in porous media as a bunch of capillaries or a bunch of parallel plates. We can look at the flow velocities you get in terms of relative permeabilities, and you can look at the intrusion pressures you have to overcome to get motion in the capillary. So we can actually link the values of these entry pressures with permeabilities. And we did that at the bottom of this sheet. So the other thing that we looked at, which pulls this all together, because we're now going to talk about unsaturated flow. We've always been careful when we've talked about this to describe things in terms of these capillary pressure curves, and you've seen this figure before. I'm going to draw this figure, but you've certainly seen it. Remember these two capillary pressure curves sitting on top of each other? That look like this, or this. This is capillary pressure or elevation in both of them. This was elevation, and I can't remember, it was red the water. This is pressure, and we talked about two different fluids. One in the vadose zone was air, and one below the groundwater table was unit weight non-wetting, unit weight non-wetting, and unit weight wetting. Water. Air. DNAPL. And the essence of what we were attempting to do was to define the capillary pressures merely by definition. Capillary pressure is equal to the pressure in the non-wetting fluid minus the pressure in the wetting, which of course, if we look at this, is the pressure in the non-wetting is this, the pressure in the wetting is this. So by definition, the difference between these is the capillary pressure, right? So, and it increases from 0 at the water table, which is here, downwards. And so we can locate ourselves on this. This is, of course, the saturation of water between 0 and 1. And depending on where you are with depth, this capillary pressure would account for this amount here. And it would define, in this case, a unique saturation of non-wetting versus a saturation of water that's left in the system. So that was the basis on which we got here. And we know that sitting underneath here, related to this, I suppose, we could think about our relative permeability curve. So that describes kind of the equilibrium saturations when the fluids aren't moving. And if we want to be able to move the fluids, then we probably have to think about a couple of other things. One would be that this cutoff here is our irreducible saturation of the non-wetting fluid. Sorry, the wetting. This is the minimum amount, minimum amount of water we can get in the system. And we haven't really kind of drawn the second curve in here, but it would come down like this. And that would define the other, which is the saturation of the non-wetting, irreducible. So when you if you fill it back up with water, you're always left with this amount of the non-wetting fluid present. And we defined these relative permeabilities, and they went between 0 and 1. They went between saturations of water of 0 and 1. And they had the form, if we use if we use green for the non-wetting fluid, it goes like this. If we use red for the wetting fluid, it looks like this. Not straight line, but that's the way it turned out. And that allows us to be able to look at the flows in the system. And so I guess the only point of drawing this diagram again, which we've seen, is to make the point that we didn't really define whether these fluids are anything other than wetting or non-wetting. We've always been careful to try and do that. And so long as we do that, we can use the curves that we took to represent flow in the subsurface for non-aqueous fluids, lighter or denser than water, to represent the same behavior we expect to have in the vadose zone, which is the topic that we plan to look at today. So this kind of encapsulates maybe the last 6 periods of what we've done, 2.1 through 2.6, right? So that should be online. I'm going to switch back to our fantastic notes and talk about what we saw. So we're talking about the vadose zone today in its entirety. And we don't have to reinvent the wheel because everything, as we've just made the point, is defined in terms of non-wetting versus wetting fluid saturations. And this, of course, is the figure that we've looked at before and we've just drawn out. So when we deal with flow in the unsaturated zone, the vadose zone, we might want to define some extra components. We can define what's referred to as the matrix potential, which is what this is. And you see that again is Bernoulli as we know it, with the velocity head term thrown away because we don't get big velocities and we don't get big changes in velocity, and so we don't get big velocities in the first place, and we might get big changes, but relatively speaking, but this term isn't very large. And the other terms are what we've called hydraulic head. But if you're an agronomist and working in the vadose zone, which is really where this discipline began, people looking at the water that would sustain crops, for instance, then they define hydraulic head in terms of as a matrix potential. And really the matrix potential really refers to this pressure head term rather than the elevation head, but it's kind of used interchangeably. So this is a hydraulic head. It's an elevation head and a pressure head. But in unsaturated flow, it's usually referred to as matrix potential because these pressures are typically negative. And so they're the water that's in tension. So to be able to pull the water up from the water table, you have to drag on it at the edges of the capillary. And so the actual stress that you have in the water is in tension. And it can reach relatively high magnitudes of tension. So it's still defined in terms of a length. The length is a pressure divided by the unit weight of water, because that's typically the fluid that we're looking at. It's a function of this volumetric moisture content, which is the volume of water divided by the total volume of the aquifer, whereas porosity is equal to the volume of water just within the void space. So but they're similar to each other. So this is a function of both either the volumetric moisture content or the saturation. And I guess I really wanted to say saturation is equal to the volume. Yeah, this is saturation, right? So the saturations are related to each other. And so we can think about things in this term. So no big deal. So if we could define capillary pressures before as equal to the pressure in the non-wetting by minus pressure in the wetting by convention, then we can just divide each of these through by this. And this is the same as PCO gamma W. So we can define it in a way. If we're dividing it through by unit weight, then it's in units of length, just as head. And so what we'll do is we'll try and use that to represent these behaviors. So if we try and unify things, it actually might be worthwhile doing this. If we draw another one of our capillary pressure versus saturation curves. And so this would be for the vadose zone. So you can think of this standing on top of the water table as we just drew it, no different. And we can label things again in terms of these characteristics. And this would be, if this were saturation of water, this would be 0, this would be 1. If this was the volumetric moisture content, then this would also be 0, but this would be porosity, right? The maximum magnitude of volume filled divided by the total. If this volume of water is equal to, fills the porosity completely, this would be equal to the volume of voids, and therefore this would be equal to the porosity by definition. Porosity equals volume of voids over volume total. So we can describe this in terms of capillary pressure. We could also define a bubbling pressure, PC0, which is equal to PB, we've called it as well. We could divide this through by unit weight. So I'm going to mouse in here. So this would now be defined in terms of a matrix potential, which is what we said before. And we could try and describe our behavior in terms of this. What we could also do is that we could change the scales so that we measure from this. So this is the irreducible saturation of water. Once the air's come in and pushed all the water out that can get out. And so this would also be the irreducible irreducible volumetric moisture content of water, W0. So that's fine. So it's a bit superfluous because we know that we really can't get entry to this part of the curve very easy, right? We stop before we get there. And so what we could do is we could think about changing the volumetric content to something that we're going to call the effective volumetric content or the effective saturation. And so all we're going to do for that is that our scale for this is going to start here at the irreducible saturation, right here. So this now is going to be 0, and this now is going to be 100%. And likewise, the saturation at this point here is going to be 0, and it's going to go to 1, and so. And the reason for doing that, if I draw this below, is if we took this curve, it's just found empirically, if we took the curve above and plotted it, instead of being on a natural scale as pressure versus saturation, if we plotted it as capillary pressure over unit weight, I drew it too close to the line, but I'm going to be very fancy. Look at this. Oh, ho, ho. Log. And if we plot what we've called the effective saturation, which we haven't defined yet, as log saturation, and that is 1, 0.1, 0.01, etc. and this is numbers, this is increasing. So if we take this green curve that we have here, and we plot it in log space, we end up with a curve that looks like this. Straight line. So these two curves are the same, but they're just plotted on a log scale instead of a natural scale. This would be, by definition, our bubbling pressure. And that bubbling pressure exists at a saturation, effective saturation of 1, which is here. And we can define this curve in terms of its slope as over 1 log cycle so this is 1 cycle, getting too involved in this, right? Just between a factor of 10, and this is lambda. So, sorry, the other way. Sorry. This is 1 log cycle, and this is lambda. And so it comes from the fact that we can write these curves in this way. So we can develop an empirical relationship, which if we take the volumetric moisture content that we're at, which is this one here, theta, if you like. If we have the irreducible volumetric moisture content, which is this magnitude here, a function of the graph. If we take the volumetric moisture content at which this is fully saturated, this is this value here, whatever that is, and write this equation, then what we could do is we could divide each of these through by this volumetric saturated moisture content. And so if we take this expression up here, this is the pressure that we find ourselves at. So this is the capillary pressure where we have this particular theta. So these are the ordinates, if you like, where we are in our graph. This is a characteristic of the porous medium, the bubbling pressure, or PC0. And it relates behavior with some exponent that we still have to see. So what we could do is we could divide this whole expression through by the volumetric moisture content when it's 100% saturated. And this actually is going to be equal to the porosity by definition. And if we do that, we'll find out that each of these terms that we have, this by definition is the saturation. This by definition is the irreducible saturation due to water. This is 1. And this is the irreducible saturation due to water. So this is just written out in this term here. Some of it's gone off the page. And so what we then could do is we could substitute this off both sides, divide both sides through by this, and we end up with this effective saturation that we said, which we've called S subscript E. And so this is a useful term to have because it really defines exactly this curve. This curve was found by experimentation, but the curve that fits this particular curve mathematically is just this exposition here. So the pressure that we find ourselves at, which would be here, so this ordinate, if you like, would be a capillary pressure divided by a unit weight, and this would be at an effective saturation. So those would be the ordinates of a particular location. This is the effective saturation, this is the capillary pressure, and these other two terms are characteristics of the porous medium. This is the bubbling pressure, which is defined by the pore throat size, and this is some gradient term that just describes the elevation of this slope, whether it's steep or shallow. And so if you can get your results to fit this, then this is the expression that we're following. That's the equation. You can take logs of both sides by logging this and logging this. Take a log of something with an exponent, it just becomes the product of that times the exponent. A log of two terms divided by each other is just the subtraction of the two logs from each other. And so that's basically where this term comes from. I guess this really says exactly what that term should be, right? If you plot everything in terms of log SE and log capillary pressures, then the gradient of this curve is just what controls it. Y equals mx plus c, except the gradient in terms of being m is equal to lambda, and it's in log-log space. And so we know that if we have this expression, when the saturation is equal to 1, then the log of that saturation is equal to 0, and this is the origin of that curve. And so at this particular ordinate, saturation of 1, this by definition has to be the bubbling pressure. So that's, if you think of behaviors as this, then this is y equals mx plus c. Right? C is this ordinate, this is y, this is x, this is 1 and the gradient. Yeah, that's right. That's just the equation of a line. And so this is just the equation of a straight line that happens to be in log space, nothing more than that. So that's kind of useful because this is a useful way for us to be able to define the capillary pressure curve. We're not doing anything other than, we're still representing this exact form, but it's just a convenient form for us to use it. And we avoided delving into it before, but it has some uses, not that we've used them. One of the uses was that we said we could get this distribution of saturation in the subsurface according to this plot. If you went through the 5 pages of derivations that give you that, which are here, which is this, then you'll see that this this equation is what's used to give you that. We don't need to do that, but it's useful in being able to describe very succinctly the magnitudes of these capillary pressure versus saturation curves. So the Brooks-Corey relationship, which we mentioned, is exactly this term here, this box term. And it allows us to define the behavior, just written out in longhand. Effective saturation equals 1, and it equals progressively smaller numbers, going down to 0.1, 0.1, 0.01, etc. The gradient of this is equal to 1 log cycle, so this is a bubbling pressure of 10 to the minus 2. It would be in units of length, either centimeters or meters, because it's divided through by the unit weight of fluid. And this represents that ordinate, and so you can describe the expression that represents that. And so that is explored here in these two figures. They're both the same, they're just represented differently. This is matrix potential, or capillary pressure, divided by unit weight on this axis. This is effective saturation. And I guess the other thing, which I drew this diagram, but I didn't really make the point, is that the effective saturation is really just this length divided by this length. So all we're doing is we're ignoring the fact that we have this dead zone here that you can't get access to. So why don't we start at 0 here and go to 100% saturation at 1 here? And if we do that, then the saturation, effective saturation at this point is this length divided by the full length. That's really physically all it is. We're just ignoring the part that we can't get access to. And it makes it convenient because we get a relatively straightforward expression that describes our capillary pressure versus saturation curve. That's all. It's just an expedient to do that. And if you look at these two curves, you can kind of pick off what those features would be. These are the 4 same different materials drawn as a capillary pressure versus effective saturation curve, and a log capillary pressure versus log effective saturation curve. So all it does is it straightens these out. It's a bit strange because it's been rotated through 90 degrees, capillary pressure on the bottom here and on the vertical here. But other than that, it's the same. So if you think about it, this is 100% saturation. And so this, by definition, would be the bubbling pressure for this particular one. So it's the pressure you have to get at 100% water saturation to first get a bubble of air to go into the system. And then once you do that, if you keep on increasing the pressure of the air, you'll progressively force more and more of the water out and change the saturation along this. And so the important thing is that if we said, what did we say? This is, so over one log cycle, so this, none of these do go over one log cycle, but I could extend this. So over one log cycle, this would be the value of lambda. So lambda says something about the form of this curve. And so if you have one log cycle and lambda is huge, then I guess the lambda ones which would be huge would be you have a small change in pressure and you get a very big change in saturation. A small change in pressure gives you a very big change in saturation would be this, right? So expression number 2 would be this. So a small change in pressure as you go from this value to this value. You get a very big drop in saturation. So that's exactly what you have here. You go up a small pressure, and physically you go across curve number 2 a long way to get to your equilibrium saturation. And so the shape of these curves is dictated by the value of lambda. So I guess this would be lambda large. And this would be the opposite. This would be lambda small. So it just describes the shape of this curve. So lambda says how steep the curve is, how steep the changes in pressure. And I guess the other characteristic is PC0 decides exactly where on this ordinate you are. So if the entry pressure is small, then that means you're probably at an open graded system. Permeability would be large, and this would be the location you are. And the entry pressure gets larger, then you'd gravitate up to these locations up here. So it's just allowing you to map between the forms. So all it is a way of being able to represent these curves in a very compact form as capillary pressure versus saturation curves. So, and this is basically saying that thing. If you have a very flat curve which represents you have a small change in capillary pressure, you completely flood the thing with air, then that's a very steep curve with a large lambda. You'd think this would be physically a very narrow collection of pore throats. They'd all be roughly the same size, so that as soon as you've invaded one, you can invade them all. And this one would start off with a smaller pore size, but they'd be much more varied in terms of their diameters, because once you've invaded one at a given pressure, you can't get into the other next smaller ones because you have to really increase the pressure to get up there. And so this would be a smaller value of lambda we talked about. So that's useful. I don't want to belabor that point, but all it is a way that we can write this expression in a relatively compact way. So that seems a bit esoteric, but it has some uses, for instance, for us to be able to define more conveniently but more complexly the saturations with depth. The other thing that you can do is you can do the same thing we've done just now in empirically relating the capillary pressure versus saturation curves, but we can use another approach. And it's just another approach developed by a different person, now 44 years ago, but still in use. And that is that these curves that we've talked about, we can define in terms of either saturation or volumetric moisture content. We know that there's a conversion between them, and so we can define these curves in either saturation or volumetric moisture content. We do the same as before. We have a residual volumetric moisture content, which is our residual saturation of water. We have a 100% saturation, which is our saturation of 1.0. This is how they map together. And based on these, we can define this capillary pressure curve as a function of these components. If it's in moisture content, this is the residual moisture content. This is the this is residual also. This is a saturated moisture content. So these are two physical ordinates. This is a property of the porous medium as well, alpha. And all it does is it allows us to link a capillary pressure or a matrix potential, either the pressure or the matrix potential, the whole thing, to whatever the volumetric moisture content would be. So we're linking volumetric moisture content to pressure, pressure on the vertical axis, volumetric moisture content at the bottom, or the same in terms of saturation. Saturation to capillary pressure or volumetric or matrix potential in terms of these other, this is a function of the porous medium, and these curve fitting parameters which are defined. We can define it in terms of the real volumetric moisture content or the effective one. And if it's the effective one, we're just starting our curve at a value of 0 here instead of a value of 0 here. That's the only difference. And we again get the term we want to define as a function of the capillary pressure and a function of a whole bunch of fitting parameters. And if we want the actual effective saturation, we again get that again as a function of pressure or matrix potential and these curve fitting parameters. And so it's just another way of being able to represent these curves in closed form. This actually has some utility because we can take these parameters, these curve fitting parameters, and we can use those to fit to relative permeability magnitudes as well, which we think are related to these curves because they sit underneath them in terms of relative permeabilities. And so these curves are just some curve fitting curves. We'll go through a very quick example. I'm not sure you ever need to do this, but the one interesting parameter that comes out of this, which operates on this alpha parameter, is actually the inverse of what we would call is equal to 1 over the height rise in the capillary zone. So remember we talked about the height rise in a capillary tube, what it would be, that a fluid would go up some amount H sub C. And if we were in an aquifer that went up some height, this would be the height of the tension saturated zone. This would be the capillary fringe. And this is also related to PC0. Right? This is the bubbling pressure. So these are all one and the same things. The height rise in the capillary is kind of the same as the HC0, which is equal to PC0 over gamma W. So these are all related to each other. So this empirical parameter alpha is in units of 1 over length, and it's equal to the height rise. So, and it turns out to be one of the parameters that describes this, this empirical relationship. So we'll talk briefly about those. There is a way to be able to figure out exactly what these parameters are, and it's just the routine that we'll talk here. I'm not sure you necessarily need to know this, but it's just a way of getting the fitting parameters from an actual capillary pressure versus saturation curve. So if you have this green curve, as we've drawn it in the past, this is pressure head, or this is PC over unit weight of water. This is volumetric moisture content. This is at saturation. This is at residual moisture content. This residual moisture content is 0.1. This saturation is 0.5. That means that the porosity is also equal to 0.5 by definition. And the recipe for pulling out this value is to first of all find the average moisture content of this system, which is this magnitude plus this magnitude divided by 2, which is this. Sorry, this magnitude plus this, so the middle range one is this, which turns out to be 0.3 in this particular case. To find the slope of this by taking one log cycle, so this is a log scale, so this is 10 to the 4, 10 to the 3, 10 to the 2. They're negative pressures, they're in tension. So one log cycle would be here to here. So draw a tangent to this curve P that goes through these curves here. Take one log cycle between here and here. So that would define this point here and this point here. And this magnitude is equal to 0.34 on this scale. So that's where this number comes from. And we're going to call it 0.34. We'll non-dimensionalize it over the length between the residual moisture, volumetric moisture content and the saturated one, which is just this length here, which is 0.5 minus 0.3, 0.1 rather. So that becomes 0.85. If we want this term m, which is one of these terms that we have here, which is this exponent, which is what we're going to get, then we get m merely by looking at the range of this value of f sub p, which in our case is equal to 0.85 from doing this calculation. It's between 0 and 1, so we put 0.85 into this expression here, do the math, and it comes out to be this. If it was greater than 1, we'd use another expression, which we don't have to do here. So we have one of the terms that define our system, which is this. If we want to get the value of n is equal to 1 over 1 minus m. So to get this, we need to know what m is. And so that's exactly this. We know this value here, I guess, is this. And so if we do that math, we end up with 2. And we also get this expression for alpha being equal to this. We have a value of m here, a value of m here, and we can get that. And so alpha is equal to this. We have m, and we have the unit weight of water over PB. And so this is the value here, and so that we know that alpha is equal to 1 over a length. So this alpha is also equal to 1 over h sub c. So what we can do is we can define each of these parameters of alpha, n, and m, and these define the components that go into this empirical relationship, which looks a bit complicated, but it's not really that complicated. So if we have values of alpha, n, and m, we can put together the volumetric moisture content or the saturation against capillary pressures that we have. And of course in this PC, this is the bubbling pressure, which we need to be able to define that magnitude. So that seems kind of a circular argument, we've got a curve, we have some fitting parameters to recover that curve, so that's not particularly useful. But if we can link these parameters that we've recovered for these curve fittings to the hydraulic conductivity, then we actually can use that usefully. And so we can also use this to develop magnitudes of relative permeabilities. And so this is just, this looks complicated, but this term here is just this relationship. Hydraulic conductivity divided by density and gravity is equal to permeability over viscosity. Remember, permeability is a material property. It doesn't change with the fluid. It's always the characteristic of the material, not the fluids within it. And so I guess you could describe this term here, just divide both terms by, and this term would cross out, right? So in other words, this effective hydraulic conductivity, if you ignore all the green type on here, is really just a relative permeability multiplied by saturated hydraulic conductivity. Depends how you define things. And so K theta, when theta equals theta sat, is just equal to what we term hydraulic conductivity. Right? So we can define, we know that relative permeability is just scale the measured permeability or hydraulic conductivity in situ relative to the saturation. So we can define, if we know what the permeability is, or the saturated hydraulic conductivity, they're related, then we can scale the effective permeability, which is where it's only partly saturated, to that just by using these expressions. If we measure the saturation, then that says exactly where we are. Again, I don't think I'm doing a great job of describing this, but anyway. What's new, they say. I'm going to draw these curves on top of each other. And so this is effective saturation, and this is 0, and this is 1. If this is effective volumetric moisture content, then this is 0, and this is porosity. And I guess all I'm trying to do is draw in here green, wasn't it? Is this and this. And so that's all it is. So the hydraulic conductivity at some particular volumetric moisture content is just a saturated hydraulic conductivity scaled by the relative permeability, which is between 0 and 1 at that particular volumetric moisture content. And so this is what we KR, this is PC, or PC over gamma W, doesn't matter which. So all we're doing, so we're choosing a value of this parameter here, SE at PC, or that's the same as a volumetric moisture content at PC, depending on how we're defining it. And we're just going down and we're defining, I guess it would be the red curve, right? So it would be the value of this magnitude here. And so we know that capillary pressure permeability will change as a function of volumetric moisture content. It will also change as a function of PC, because PC changes volumetric moisture content, so they're linked. And so we can define the relative hydraulic conductivity either in terms of volumetric moisture content or head. They're linked through this arrangement. We can either define it directly through saturation or volumetric moisture content, which is easiest because we just need to find this location on this curve for that particular value. If we're defining it in terms of head, we have to figure out exactly what the head looks like, the magnitude of head. That gives us saturation, and then that gives a relative permeability. So I guess it's going left here, going down here, and then going across. But they're related. And so in either way, we can define exactly what the hydraulic conductivities are. And so the utility of that is that if you have magnitudes of these parameters, which are m, n, and alpha, which are defined as a function of materials that you might find, which are classified as sands or silts or clays, then perhaps you could do that straight away to throw them into this and get these relative permeability magnitudes and capillary pressure curves that we talked about before. And so that actually is the case. And so, I'm not sure this fits all in one place. These are called these Van Genuchten parameters. And the values of these are that this is, if I put in what we've talked about, this is what we've called our saturated moisture content. This is our residual moisture content. This is what we've termed alpha, and this is what we've termed N in these, just a different term here. Then you actually have values for each of these terms to be able to substitute back into this. So if you know, for instance, you have, I don't know, a sand, which is this one here. You have values for the saturated volumetric moisture content, the residual volumetric moisture content, alpha and N. And so if you want to determine exactly what the value of either K as a function of volumetric moisture content is, or K as a function of effective saturation, you merely go back to use those in the appropriate expressions. So this is here. You had a value of alpha. You had a value of N. And you know that N is equal to 1 over 1 minus M. So from this, we had value beta is equal to, it's out here. So if you have, we each have values of N and alpha that describe the system. If you have N, you can calculate a value of M, so you have M as well. So you have all of these terms that you need to be able to fill in this expression. Not a very simple expression, but you have everything you need, and you get the value of permeability, hydraulic conductivity, as a function of either head or as a function of effective saturation. So you're able to describe exactly this curve. Likewise, if you have these values of n and alpha, you're able to substitute it into these expressions here and get the capillary pressure versus saturation curves. So you don't need to do an experiment to define those behaviors. You can just rely on the fact that someone has classified them based on a variety of different soil types that cover a broad range. Clay, very low permeability, sands with relatively higher permeability, no gravels, but at least you have a substantial range of these characteristics, and that allows you to be able to define exactly what those terms are, which we spent really the last 7 weeks really trying to understand in some detail. Right? So that's it, I think, for today. And so it all stems from the fact that this diagram, this is an important diagram for us to kind of understand in microcosm. So from now on, if we zoom back to what we've talked about before, what we'll spend our time talking about is we know what the architecture, what controls the architecture in this geometry in the subsurface. We know that capillary forces are very strong and will hold it there unless we work very hard to suck out the free product, which we probably can't do very well. We also realize that if it's not going to move, then we shouldn't perhaps worry about it. But the problem is that these things, that although they are very low solubility, the solubility is finite, and I guess their toxicity is high at very low concentrations. So in these little cartoons, you see these stippled areas shown are just the portions of the dissolved plume that migrates downstream. So what we're interested in doing now is we'd like to know that if we know what the architecture of the material is that's in place and is stuck there, and if groundwater is flowing past it and is able to pick this some stuff up at some kind of concentration, really the second question that you're doing in your assignment number 3, then what is the plume going to look like as we go downstream? You've already done some things to look at exactly what it would look like in terms of this simple plug flow type models for the stuff that's carried downstream. But what we'll find out is that these plug flow models aren't accurate for all conditions that we could imagine. And so we haven't dealt with that yet, but we will do. And we'll find out how we resolve that dichotomy to be able to look at real systems where we deal with this. So we've covered all we need to know about the initial motion of the multiphase fluids. They're stuck in place. Now everything we'll talk about will be dissolved components. First to talk about how it gets transported in dissolved form downstream, and then to talk about how it might be sorbed and attenuated as it goes downstream to lessen its concentration as it arrives at some kind of compliance location downstream. And then we'll talk about finding out how you characterize the subsurface and then how you remediate it, which is what our last parts are.